Okay, let's say that we'll say that we can start. First of all, I introduce myself. I'm Andrea Morichetta. I recently joined the TU Wien and the DSG group. I arrived in January, so it's 3 months now that I'm in the DSG group, and as a university assistant. And so this is my first time lecturing in TU Wien. This is my first time also as a YouTuber. So let's see how this goes with live. And I come from a kind of different background. I come from networking and machine learning. So things are kind of new for me, and it's gonna be, but it's nice to have the chance to explain these things and have this lecture. So, okay, I think we can start with the presentation. So, what you have seen the last time with Thomas is basically how complex some applications, some systems are. We had the example of Netflix as a very complex system, and now also managing the complexity is fundamental and important to give an interface and give let the system work with less complexity and managing it better. We have seen concepts like layering and abstraction and generalization and how they work. And as well, we had an insight on how we can structure databases and how we can do basically concept of polyglot persistence, so we can able to break the monolith and be able to express and give different database models depending on the different application that we want to manage. Today we're gonna see something more in the direction of service oriented architecture. So we see how we can split the whole and unique application in multiple services, and how we can let those services interact. And so we're gonna see interaction models like remote procedure calls, service-based ones, and message-oriented. In the end, we're gonna have an overview of the microservice architectures and also new trends in this field. Okay, so what are we talking about when we talk about a monolith? A monolith is the unique system in which different models has been built together, and which they solve different functions. But this can work, but however, the problem is that when we want to scale up, it's difficult to maintain this kind of services, and also it's difficult to understand where is the problem, what and who generated the problem. So that's why we need to break the monolith, and we can do that through the concept that we have seen in the first lecture, so through the composition, abstraction, layering, and generalization. So we can build groups of services that are coherent between each other, and they can interact together in order to kind of rebuild the functionalities of the huge monolith, but in a distributed way. So here then what we are proposing is to develop a service-oriented architecture. What is a service-oriented architecture? It's made up by those services that communicate with each other, not anymore inside the same application, but they communicate through network via interfaces and protocols. Those elements, those services are loosely coupled. That means that they can work independently, so they don't need to refer so much to other services. And this is good because it allows us to work and update and control the execution on on these single services, and how to split the services and to split the monolith is also creating some boundaries. So creating some context in which the services can be self-contained. So basically we can work on the code for that context without carrying and knowing details of other parts of the system. So what is the service-oriented architecture? It's made by, as we've seen, services. Those services have some important properties. For example, the first one, that each service logically represents a business activity. So it's also something that we've seen before, also with layering, and so logically build business logically similar blocks. It is self-contained and can be seen as a sort of black box because we don't know the internals. Those services can in fact consist on sub-services that we cannot see, and what we can see as consumers is just an interface that of those services that we can interact with. So how can we think of a service-oriented architecture? This is a sort of general abstraction where we have a service provider that has this business logic and publish this service on a registry. The consumer can then discover the services and bind to the service provider and start to communicate to get the procedures and the functions that this service provide. This should sound as a familiar structure because in fact we can project it to web services, where web services through the WSDL can be described in those web service registries, where the web client can look, understand what the service provide, and then start communicating and binding and communicating. It's also something, the same structure can be applied also to RESTful web services when this role is the role of organizing it is taken by the API gateway that is providing the interface, and the web client interacts with that and then binds and communicate with the RESTful web services. The same is for JPA, and you all know Spring, so the concept is similar. So we have interfaces and instances of interfaces, and we communicate in this way, and we are able to then through these interfaces communicate with the server. So as we said, services work in a way that is distributed. So the functions of a system will not be all at the same machine. So we need to communicate to different machines to get function and get procedures. So what we need is a way to interact between different services that have different operating system, different languages, and so there's the need for something that allows us to easily communicate. The first thing that you're gonna see is remote procedure call. It's something that you already have seen, most likely. So you know how it works. Remote procedure call, we can say, they work as a sort of middleware where we facilitate the interaction between client and server. So the elements that we have here is a client, procedure that is on the server, and a middleware that let the client to perform a remote call to this procedure and get the response. This is how it works more in detail. So if I'm a client, I'm calling for a procedure that the service has and provides. What we need is, you can see between this communication we need some object that allow us to let those two, the service and the client, to communicate. This can be performed, it's performed in remote procedure call by those objects that are called stub and skeleton. One is stub is resident on the client, and the skeleton instead is on the server side. What the stub does is basically to marshal, so serialize the call in a way that is independent from the client and can be univocally understood, be understood by the server. The skeleton, on the other side, what it does is to take this request and marshal it, giving it to the server in an understandable way for the server, that will perform the operation, the procedure, and will return the result. And again, we can then the same path is done backwards up to the client that receive and the response to the procedure that it called. The concept of abstraction that we've seen in the first lecture can be very well applied also to remote procedures calls. Remote procedures calls can be the lowest level of abstraction. So we have server that provides some procedure, and the client that accepts can call those procedure through a unique interface. We can add one level of abstraction here. This is can be introduced via the object-oriented abstraction. So we can create object, and this can be done through Java MI. And so we have data and methods that the service provider and the user and the client can interact with. We can also provide a upper layer of abstraction. Here we go to the business logical abstraction. So we have a component. The component is basically can be seen also as a group, as a cluster of more objects that solve and to same operations, and can allow to provide better abstraction, a better re-implementation, but on the other side it adds a new level of complexity. And finally, we have the service-oriented system level, where we basically see the system as overall as the business ensemble, and allow to a better standardization, a better understanding, but it also covers and hide all the details of the other layers. Remote procedure calls can be implemented in different ways. Can be language specific. So as we've seen before, if we refer to Java MI, so the remote method invocation, we can have it in Java. There is the version for Python, but can also be language independent. So using, for example, plain text or binary transmissions, like gRPC that we will analyze later. So an important step of remote procedure call is to marshalling is the concept of marshalling. Marshalling consists in providing a structure of a object that is in a language that is interpretable and transmittable to the server, and can in then perform the procedure that we want to perform. For example, here we have an object that is a person, in particular Barbara. We have the variable last name, first name, and age that we can translate to the masher into a JSON that looks that looks like that. We can, of course, implement it also in XML or in language specific use. For example, this is the output of Java object in RMI. As we've seen, if we have an abstraction in terms of object, we can send methods and requests and procedures in and we can see them as objects. So, for example, here there is the request that is calling for a procedure that is asking for the information of a user, looking at her name of this, looking at the name of this user, and this request can be marshaled in a way that we see, like here in the bottom left side. So we have an information about the JSON, we have the ID of the request, we have the name of the method and the parameters that we're passing to the function, to the method. And on the right side, we can see the response. So we have the result, the idea of the response, and this is structured in a JSON structure, like in the dictionary structure via the JSON. So this is an example of our remote procedure calls middleware work. So we have an interface to the person directory. We have a person that has some feature, like let's say last name, first name, and age. We have the DB person directory that is referring to the structure of the database that is used to store this information. And we also have the stub, that is is where the client interfaces with, is what the client interfaces with. So the client can, the stub of course have a marshaller that puts translate the client request for a procedure in a way that is understandable by the server. The client can interact with it and request and send a request to the servers. The request is then shipped and is then handled by the server through the skeleton that we've seen before, that then marshals the object that it has received, contact the DB, the database, get the information and send it back to the client. So these are pseudo implementation of the stub, pseudo implementation of the stub and the skeleton. This is the stub, and it consists of as we can see, we have a class that is the DB person directory, that in this case is implementing the function find by name for the person. The stub that we can see here has two objects, the RPC client and the marshaller, and we have a method that it's find by name that returns a object person. It basically instantiates a new request that is find by name, and this request is marshaled through the marshaller, and then RPC client takes care of sending the request. In the end, there's gonna be a method in the return that will unmarshal the response that we will get from the server and return it to the client. So on the other side, what is happening is that the skeleton object will have a response, it will have a request method that it's returning a response, and basically what it does is to get the method, if the method is equal to find by name, and will marshal the request perform on the real implementation, so on the implementation of the person, the method find by name of the name of the person that we want to find the details to, and then it marshal the response and send it back to the client. Here we have seen a certain implementation of this skeleton. Are we able to generalize this? Yes, we can. This generalization can be performed in different ways. So via templates and generation of interface description, as we've seen before, as we will see later, with gRPC, or via dynamic proxy. So we will see more in lecture 3, but basically we have invocation handler that manage with the different procedures that we are going to refer to, and it basically is a mimic of an interface, but it actually calls this object. So what we will have to do, for example, is to define the method I want to call and send also the arguments. So we're invoking. We need to invoke the function and send also the arguments. What happens, however, when we have faults in the process of remote procedure call? Those faults can happen on a different level. For example, in the server part. And the problem here is that if you're not, if you have a different language, we cannot know how and when the error appeared and what the error means. So again, we have to refer to a different concept that we've seen before. That's the concept of abstraction. So what we're doing here is to try to understand and specify, and this is what the XML RPC specific or JSON XML RPC specification for fault interoperability do, is to find a way to provide a unique interface of an abstraction of the error that can be understandable independently from the language that is used on the server side, and can be then understandable and interpretable by the client. So those, for example, are codes of errors that are defined by the specification for fault interoperability, and here we can see an example of a method not found that is -32601, and it's giving a general description. Is something like something we will see later on HTTP errors, which are unique codes that can be interpretable on the client side. So then we have seen that we can are able to or clients are able to request or to call procedures that the server provide to remote procedure calls, and there is a mechanism of sending the request and getting the response. However, we have to define the way for transporting these messages, so for transporting these requests and response. This can be done in two main ways. When we have to deal, for example, with text like JSON or XML, we can use, for example, HTTP. Yeah, this is the technology underlying the web services, and using HTTP allows to, of course, use existing high-level transport mechanism. It's easy to understand, also debug and develop. On the other side, it adds, being also an high-level transport mechanism, it allows additional transport overhead. Or when we're dealing with binary stream, we can refer to TCP or UDP. Of course, here we are faster, we have less overhead, but on the other side can be also another advantage, can be very well optimized for a specific input and output. But on the other side, this means that we have to develop the solution in a more detailed way. We have to be very rigorous in the specification, and we have to manage the communication and all the underlying things that HTTP instead doesn't require to deal with. So our packets and the communication has to be performed. So in general, when we're dealing with remotings, the principal components are the ones that can be summarized by this slide that is basically what we have seen up to now. So we have a client, we have a proxy that works as an interface to the procedures, and what is a remote object that is staying on the server. We have an object that takes care of dealing with the request of the client, and that it can be then transported and then handled again by the server that then calls the invoker that actually invokes the request and the function, the method, and give the reply. In the middle, there are all these actors that are the interface description. So, for example, we have an interface that describes what the server does, what are the services that and the procedure that the server provides, and also what the client has, and how the client is structured and what the client supports. We have marshallers, and then we have also the way to deal with remoting errors. So we have also those actors in the middle that takes care of making it consistent and make this process work smoothly. So as we've seen before, we can use specific technology. For example, we have gRPCs has been developed by Google and provides a way to build an RPC, to build remote procedure calls. This can be performed via using different languages. For example, the main ones are Java and C, and then there are all the implementation possible, like with Python and all the other languages. So it's possible to define a service and define requests and replies and messages, and then the gRPC will take care of generating the code and generating all the information that are allowed to interact between client and servers and to perform the remote procedure calls. So for example, here we can see what we have seen before, the stub and the skeleton, basically, so we can handle the request in this way. So and also as well as getting performing the procedure and then responding. So we can handle all the all the different blocks that we have seen before with remote procedure calls in this using gRPC. Going on, wait, we have questions, okay. What is an application like, exactly? Yeah, we probably have answered before explaining it. But if there are questions, then we can deal with question afterwards, or just sending us email after the lecture. So the second way we will see how to interact between services is the service-based interaction model. So again, this is a recap of what a server is. It's what we've seen before. So it's a business activity. It is self-contained and performs some procedure and some functions that can be accessible to an interface to clients, but it's not fully visible, of course, from the client side. Here we will talk about web services. So web services are a way to develop loosely coupled distributed systems. So web services allow a communication between different devices that are so different machines that can have different platforms using different programming language, different operating system, and can be categorized into general types. We have the big web service one that is made by a SOAP or WSDL that we can see later, or via RESTful web services. So how the SOAP WSDL implementation of a web service work? We can see a structure that is pretty familiar now, because it's a structure of system service-oriented architecture. So we have a service provider that publish the description on a registry that can be accessed by a consumer via SOAP. That is a way of interacting with the registry. Can read the description of the procedures that are provided by the provider, and then can eventually bind and start to communicate with the service provider. This part is called on top is called service discovery, because it actually consists in publishing a service and as from the provider point of view, and then from the client and the consumer looking at the registry and find the service, understand what are the function that it has and the procedure that it can perform. Here we can see an example of SOAP in an XML. So we have the envelope that's basically defining the general features of this SOAP, so the kind of encoding and general information. Then we have headers that are not mandatory, and we have the body that is actually containing the messages that has to be that have to be sent in the communication. On the other side, we can see also in this slide we can see how WSDL look like. So WSDL is basically a document, an XML, in this case that describes the services, so describe the functions and methods that the service provide, and that can be accessible by the client. So can look a little bit hard to understand, but it basically contains all the information in the client that can be used then to interact also with the server. The other type of web services that can be developed is using REST. REST stands for Representational State Transfer. But what is REST? REST is not defining a protocol nor a standard, and it's not a technology. What it is like an architectural style, so a style for distributed system, and emphasize and run on the definition of some protocol and standards that are, in our case, the HTTP, the verbs that are typical of HTTP, for example, get, post, put, delete, and some structure, so the structure representation of the information via XML or JSON, using URI to indicate some resources, and it's fundamentally based on resource. In fact, the characteristic of REST is that is a resource-based interaction model, and it can be seen in this slide. That we have the REST API for GitHub, and we have some parameters and definitions of parameter and types. But how it actually works is that we have a URI, so a resource, and we have parameters that can be accessed to that specify the path. Like we can say that we can interact with the service, and we can get and understand via the specification of parameters that are available on the path, and on queries that are also available when binding a request. For example, a GET. So here, for example, is what we get if we ask for a Google user, and we look for a repository, and we sort by the update date. So the key characteristics of REST is that is resource oriented. So basically, the definition of the architecture is based on the is centered on the concept of resources. So also when we define paths, we define paths to resources, and we have the traceability is performed via the URIs, so the unique resource identifiers, and we have a uniform interface that is the HTTP interface. We have also other characteristics like the fact that it is stateless. So the state is basically carried by the request, and exactly the server doesn't store information and context about the client. And also it's possible to layer it through and work through over caches using gateway and proxies. And for example, if we think of API gateways, basically redirect the actual services redirect to services the request that the client performs without knowing and having the overview on all the different services that a system provides. So here we can see the HTTP interface, and as some key characteristics that some of these methods and the verbs that are typical to the HTTP provide. So we have safety, so that means that there are some functional methods and requests that are safe if they are just getting data without or just interacting with the server without modifying the content that is on the server side. We have a concept of requests to be in idempotent. That means that if I perform multiple times same request, I should get the same result. It's obviously not true for all the verbs. For example, it's not true for the post, but it's true for get and delete and put. And also, we have another characteristic that is the request body. Theoretically, all those verbs need to have a body. Actually, what it happens is, for example, with get, we put the information, as we've seen before, in the path and in the and using the parameters when sending the request. So you're actually not using the body. So again, if we think of the structure we also have seen and analyzed before about the need for an abstraction and for the analyzing and managing remote errors. Here we can see something similar. HTTP status code is the way that HTTP has to communicate what is happening. So here we have different status that can be divided and grouped according to different codes. So the codes that start with 1 usually they mean that there is something on hold. If they start with 2, everything is okay. So they usually are for successful requests. The most famous ones are, for example, client errors that are the group who starts with 4, or the server errors that are the one that starts with 5. How though can we define and specify what are the endpoints, how the message should be transmitted, what are the types that are allowed to be returned. The specification can be performed with documentation as code or via specification languages. So here, for example, we have the documentation that explain basically how the API works and what the API allows, and what's the type of the response and or of the request if you need to send a request of a certain type. And it allows us to have allows the client to have a view on the definition of the service and of the system. Via code, it's possible to, for example, the JXRS, that is an API provided by Java, that allow to specify RESTful web services. So it basically works with annotations, and as we can see in the example here, we have for example, the user directory and the path that specify the user directory. If you want, for example, to get a user information via ID, or instead how to define methods for finding a user by a name. So that is the implementation of the definition of the structure and the specification of this RESTful API that allow us to get users, and this it's how it will work. So we have the URL, we have the path, parameters, for example, here the user and the ID, the category user and the ID, and here we have, especially if we have to find a specific user, we can also define parameters, query parameters. For example, here we can specify the name and send a get and get the response again from the server. Another way is to use Open API specification. That is basically providing a schema, and is useful for generate documentation and also clients. And as you can see, it specifies all the properties, the type, and the parameters that are specific for the API that we are defining. Here we have seen now REST and RPC. Those are ways to an approach that allows us to make service communicate remotely. So we have a client, we have a service, we have a way to communicate. However, as we have seen, the focus between REST and RPC is on different. Is very different. So there is we cannot say if RPC or REST are if it's better RPC or REST. It really depends on the application and implementation that we have to perform. So it's also possible to combine both of the style, and the characteristic is that if we are deploying RPC style service-oriented architecture, we have to focus on the description of the interface, so the parameters, how to serialize the marshaller and the marshaller, and how we transport the information. With REST, we have to focus on the resources in the definition. So it's a very resource-oriented definitions, and the operation connected to those resources. So it really depends on what we have to perform, and and what we have to implement. Finally, we will see another way of interacting between services, and is the message-oriented interaction model. This model, it's basically answering a question that is the and a need that is one of the coupling between space, time and space, the applications. It's based on two main concepts. There's the concept of messages and channels, and can be naturally event-driven and asynchronous. That means that we can, in this way, also decouple and answer to the need for time and space decoupling. An important characteristic of messaging interaction models is the fact that they have queues. The queues are fundamental because with respect to what we have seen with remote procedure calls, they allow the sender and the receiver not to be always active and at the same time. So it allows exactly to decouple and to the activity of sender and receiver. So using queues, you can basically the different actors interact with the queue. So putting messages in the queue, receiving messages from the client side, for example, and also we have a poll that is a way to check if there are new messages in the queue, and also notify if we have an event handling way of dealing with messages to call to notify basically the receiver when a message has arrived. As I anticipated now, the way we can deal with messages and in this model is via polling or in an event-driven way. So with polling, there is an application that constantly or regularly, better said, checks if there are new available messages. On the other hand, there is also the different approach, that is the event-driven approach. So it's basically there is an asynchronous notify when the message is received, and it can work also to run multiple notify consumer that basically can, via selectors and trend multiplexing, allow different actors to receive specific messages. When we have a communication, we want to be sure that only one receiver will get document or will perform the call that we are requesting. In the messages model, we can build and deploy a point-to-point channel. This channel is basically creating a univocous communication between the sender and the receiver, where all the messages are sent and the requests performed. There is also the possibility to for multiple consumer to listen on the same point-to-point channel. This can be performed via what is called competing consumer. So there is a queue and it's a channel where messages are being sent by the sender, and there are consumers that are competing for getting a message, and only one consumer will get a message. So there is basically in the end a messaging system that decide which consumer received what message, and usually there are many ways that this can be performed, but typically this is performed via round-robin mechanisms. It's also possible, however, to broadcast an event or to many multiple interested receivers. What means the concept of interested receiver? That means that we go back to the definition of publisher and subscriber. So there is a system that provides some services, or in this case the publisher that publish some events that can be relevant for some subscriber, and the subscriber can decide what it can get. What the publisher does is to advertise these messages and sending them on the channel. For example, we have an example where is notifying that the address is changed, and there's a subscriber listen to this channel, but they can also decide not to listen to everything, but they can listen or either on specific topics or filter the content. That means that we have those two basically concepts. There is the topic-based publish-subscribe model and the content-based publish-subscribe model. The first one, the publisher publishes the message and gives the information of this topic that the message refers to. And whereas in the content-based model, the publisher just published the message, and there is a filter that then is performed to filter the content of the message and allow the subscriber to get the message if he's interested in that. As we've seen in other cases, how to interact and interface to this messaging mechanism can be performed through different middlewares. Those middlewares basically implement logic behind interfacing the message interface model, interaction model, and we are seeing many that we're gonna explore more in lecture 5. For example, RapidTimeQ, and what those middlewares do is to again provide an abstraction for the for in this case the interaction, so an abstraction for reducing the complexity of the distributed system. Because if you have a service-oriented architecture where we have different systems that have different communication technologies, the message format can be very different. We have to open potentially now and basically n square of communication. Instead, through the definition of a middleware, all the services refer and interacts with the middleware that then takes care to communicate and send document or request for procedures or response to the services specific having a unique specification and technology for communication and messages. This is obviously reducing the complexity, but is adding an additional architectural component. There can be define different protocols that are basically providing an interface to the middleware. So those protocols, messaging protocols, provide information on the and specification for the format of the message, the primitives for sending for procedures and events, and how to manage the connection, and also they provide also other information. There are many different notable protocols. For example, we have the AMQP, that is our open standard protocol for middleware, for message-oriented middleware. There is a simple mail transfer protocol. This SMTP is a famous protocol for messaging and interfacing with mail. And what is important here to underline is how those protocols exactly, as we've seen just now, they contain all the information and they specify the definition of the interaction with the middleware. So those are two different protocols that have different syntax to perform and interact and send messages and perform the interaction. So basically this is what can be provided via this messaging protocol. So the clients that communicate via this protocol can have an interface, and the middleware basically takes care of handling all those different protocols and allowing the communication between different services. So what we've seen up to now is how service-oriented architecture is generally structured, what are the ways of and how can we interact, and how we can let services interact with each other when being on different machines. And but how can we define an architecture? So how can we define a service-oriented architecture? Through the time, we had to think of different ways to perform that. In the beginning, there was not really a clear way of dividing services. So with many functions that were replicated many times, and making what can also be named as a sort of spaghetti-oriented architecture. Afterwards, in early 2000, we started to think of layering the monolith in different business logics that we've also seen in the first lecture. So providing different levels of abstraction and incrementing the reusability and giving a vector structure, architectural structure of the services. Recently, what we're providing is definition of what is called microservices. So the monolith is broken in multiple services that interact with each other, and they're self-contained, and they are loosely coupled between each other. So, given also technological changes that we had in the last years, was also possible to achieve this structure. So going from a unique monolith that is performing things also in a redundant way to a better structure monolith to, in the end, very let's say a structured architecture using microservices. So, as we've seen, again, the definition of a service is a business activity. It must be block contained. Self-contained is a sort of black box, and but what does it mean? This in reality. So, when we are deploying or developing an application, we can thinking of logically divide and logically separate different parts of the application. So, for example, if you have this application is Music Corp application, we can divide catalog from the warehouse and recommendation. So we can create different layers or different abstraction for the different logical parts of the application. This can be logically or theoretically self-contained, like in each part can be really self-contained. But again, then when we're looking at it, we are referring to all those elements refer to the same database. So in the end, the abstraction and the splitting and separation is made only logically, because then architecturally you have the same, you refer to the same DB and the same single point. But again, it's also possible that even if we divide very well logically and we create context boundaries, so we're able to define a business context very clearly, it's still not to give for granted that we don't need to interact and to have a sort of coupling with other contexts. For example, we need for the finance to refer to the catalog, so we have functions that have and procedures that have to refer or database structure that have to refer to the catalog. So it's not really easy in the end to have a fully self-contained systems. But this is the idea behind microservices. So providing the characteristic of a service, so having a high cohesion in terms of architectures and models, and dividing very well the different contexts. So for example, we can have the API for the management of the passenger with its own database, and the same for the driver, the same for trips. So we have all these very well self-contained microservices, but still at this point we have to make them communicate. So what we have to do is to perform communication and make them communicate one to each other. So how do we perform that? So if I'm a client that I have to interface with a service that is architecturally built using microservices, so system that is logically built with microservices, do I need to know all those how all those services work, how to interface with all those services? This is not easy, especially in some cases can be, for example, when dealing with mobile clients, it's not possible to give this visibility. It's too complex, it's not always manageable by, for example, the client, especially if it's a mobile one. So we need a way to again simplify and reduce the complexity. How do we do that? We can perform that using an API gateway. What an API gateway fundamentally do is to hide all the structure of microservices, and it takes care of communicating and interfacing with the services, and getting the requests from the clients, giving response, and sending messages to execute procedures. This is why an API gateway can also be called as a sort of chat interface, because it basically most of the work is to communicate with the different microservices and perform a gateway itself, an interaction between the client and the servers services. This is not always good, because again we are having a single point of interaction, and the API gateway has to deal with all the services, so we have to find a way to make it better, and this can be performed for again using the same concept of abstractions and layering, and this can be performed in this case by providing different interface for different front ends. For example, we can have the one that manages the mobile interfaces with the mobile applications, the one that managed with the customer website, and also the part that is has to deal with the management and the management of the back end. So those structures can be really useful, can allow us to have a better definition of the different system, but on the other hand, we need a proper way to interface them in order of not giving to the client, having the client have all the information about the system and not to overloading some layers of the architecture. So what we've seen today is basically what a service-oriented architecture is, what is theoretically, how it can be implemented. We have seen different ways of models for the interaction between remote services, so services that do not live on the same machine. We have seen remote procedure calls, how they work, concept like marshalling and unmarshalling of requests or procedures, and we also seen how this can be technologically implemented and generalized. We have seen web service implementation. Briefly, we introduced the SOAP WSDL schema, and as well as the RESTful web services, understanding what is the way of implementing it, the differences between REST and RPC, and in the end we have seen messaging systems, interaction models, how they perform, what is the concept of a middleware, and how this middleware allowing to interface different services. In the end, we describe architectures and how the architecture of a system changed during times, the concept of microservices, and how this microservices structure and architecture can be implemented in real applications. With that, I'm finished, and for any question about the lecture, we can send an email to me, we can talk about it. You will find this lecture